Okay, let's do a couple more examples involving conservation of mechanical energy. And again, for each of these examples, I recommend you pause, give them a try yourself, and then we take it on together. So you'll notice in this question right here, we have some beginning information over here, and we have some final information, and something complicated happens in between. And in order to compare those two, essentially the idea is something has to stay the same. And in this case, it'll be mechanical energy. So that's how we can recognize when to use it. Let's set this up. So let's do conservation of mechanical energy. So total mechanical energy initial, or at A, I can be even more specific if you want to, is equal to the total mechanical energy at C. So we're saying that, just make sure we're clear about what we're saying, is that if we added up the total mechanical energy and we found out it was, let's say, 200 joules here, well, can you see that it would be 200 joules here, and here, and here, and also here? It stays at 200 joules the entire time. So that means we don't care about what happens in between because we know the total mechanical energy will stay the same. That's the power of conservation. But remember, this isn't always true. We need to state our conditions here. So over here, let's state the condition. And once again, we say that there's no friction, no air resistance, no energy loss due to heat and sound. And if you want to be really thorough, you could say there's no motor in this vehicle as well to propel it. But it's a roller coaster, so they don't have motors. Okay, so there's our setup. And again, let's just list all the mechanical energies. So we have EK at A plus EP at A equal to EK at C plus EP at C. And recommended, just write down all the formulas. So let's go through the list here and see if anything can canceled here. So first of all, is there any speed at A? Yes, there is. So that one stays. There's definitely kinetic energy. Is there any height at A? Well, again, it depends on where you establish your reference height. But since everything is being measured from here, from D, we'll call that our zero height location. And therefore, it does have height, so there's potential energy. So nothing gets canceled at the beginning. At the end, we're looking for the speed. It's kind of our goal in this question. So there's going to be kinetic, and there's also height. So you notice that nothing gets canceled in this question. But in this question, we don't know the mass. Good news is you don't need to know. Because again, you can divide both sides by mass, which effectively turns into dividing every single term by mass, if you remember that from algebra in math class. And you'll see that the masses cancel. Masses cancel, mass cancels, and there we go. So we're left with 1/2 VA squared plus GHA equal to 1/2 VC squared plus GHC. And really now it's just plug and play all the way through. I'm just going to plug the numbers in here. We have VA, which is 4.5. So 4.5, don't forget to square that, plus 9.81. The height at A was 8.6. 1/2 V squared, what we're solving for, and 9.81 times the height at C, which is 5.9. Yeah, and then we just do some algebra. So I'm just going to do some sub-calculations here. So we get about 94.491 equal to 1/2 v squared plus 57.879. Okay, I'm sure you guys can do the algebra, so we'll just quickly go to how we will get the answer. You show as many steps as you need to. And sig digs looks like 2. So I get about 8.6 meters per second. So while you're waiting, I'd recommend you actually take on the next question as well in your workbook. And this time we have springs involved. So feel free to pause, give it a try, and then we'll take it on together. Okay, so again, we have some before information, we have after information, and something complicated happens in between. Classic for conservation. So let's start out the same way. We write out conservation of mechanical energy. We're going to go a little faster now. So if we do EM initial equal to EM final, and we start doing our list, so we have EP initial plus EK initial plus ES initial. So now we have all three is EP final plus EK final plus ES final. Let's now move our way through this and see if we can figure out what things might cancel out. So we start with EP initial. Is there any height at the beginning? It's kind of what we're looking for. And so we're going to let this be our reference height down here at the bottom. So there will be potential energy at the beginning. Is there any kinetic at the beginning? Well, that means it has to have speed, and there is. Good. Is there any spring energy at the beginning? And it's not in contact with the spring yet, so the spring doesn't play a role at the beginning. So there's just potential and kinetic, height and speed. At the end, you'll notice that it comes to the reference height. There's no height, there's no potential energy. We're told that it's going to come to maximum compression. That means we've compressed the spring as much as possible. And if that's the case, that means this cart had to have come to rest. If it's still moving, it would keep on compressing the spring. Therefore, there's no speed at the end, there's no kinetic energy at the end. But there will be spring energy at the end, since you've compressed the spring. Okay, now we can put the equations in for each of these. So mgh initial plus 1/2 mv initial squared equal to 1/2 kx final squared. Now I want to make a really important point here. Can you cancel the mass? If you tried to cancel mass, you have to divide every term by m on both sides of the equation. And notice it cancels from the left-hand side, but there's no cancellation on the right-hand side because there's no m in that term. So m's don't cancel here. And this is why in this question, I had to give you the mass. So you do not want to cancel m's. Don't just start hacking m's because you feel like it. All right, let's make sure we go with standard units here. So the mass is 0.25 kilograms times 9.81 times h plus 1/2 times 0.25 times the initial speed, which is 3.8, and don't forget to square that, equal to 1/2 k. The spring constant is 276 newtons per meter, so 276. And we're told that it has been compressed 16.2 centimeters. That is x, how much has been compressed. So that would be 0.162. Again, don't forget to square that. So once again, we'll just do some sub-calculations here. So this is 2.4525H. That's 1.805. And this will be 3.6217. And then we can go from there to solve. And sig digs looks like 3. So I get 0.741 meters, or 74.1 centimeters. Okay, now you've seen it all. So you have enough information to be able to solve the rest of these questions. Good luck on your homework.